here. All right. Now, what force would be required to keep what force would be required to keep this slab in motion at constant velocity? Well, constant velocity, that's going to be a kinetic case because now it's moving. So let's go back up and see what is the kinetic coefficient of friction. It's 0.67. All right, so there's less friction involved here. So let's see, what force would be required to keep it moving at constant velocity? Constant velocity means the acceleration is 0, which means the net force is equal to 0. So again, the force of friction and the applied force will be equal. So let's solve for the kinetic case here. I think, what did I say, 0.67? I think I said 0.67 times 2,452.5 newtons. All right, if I multiply those together, I get a force of friction. Now, if it's moving, there's less friction, 1,643.2 newtons. So the applied force is much smaller, right? You got to apply 2,084 newtons to get it moving. You only got to apply 1,643 newtons to keep it in motion. All right, so those are a couple of really great friction examples. Let's now take a look at the inclined plane. So here it says on an inclined plane, a trunk weighs 562 newtons on an inclined plane inclined at 30 degrees from the horizontal. Find the components of the weight parallel and perpendicular to the plane. All right, so I'm going to draw my plane here. Here's my plane. Zoop, zoop, zoop. And I know that this angle is 30 degrees. Here's my is it a trunk? Yeah, my trunk. Okay. And the force of gravity, of course, points straight down. So the force of gravity we have is 562 newtons. I also know there's a normal force which points perpendicular to my surface, Fn. So we want to find the component of the weight parallel and perpendicular to the plane. So I can think of this force of gravity here as having a perpendicular component that points perpendicular to the plane, and one that has a parallel component which points parallel to the plane, Fg parallel. And if this angle is 30 degrees, then this angle is 30 degrees as well. And so this boils down, if you look here, I've got a right triangle where the force of gravity is the hypotenuse of the right triangle. And I have a component that points perpendicular to my plane. It's in this perpendicular direction. And I have a component that points parallel to my plane. It's in this parallel direction. So we can solve for these two components. Let's see, we'll solve for the parallel component first. It's opposite my angle, and I have my hypotenuse. So opposite and hypotenuse, right, we're solving for the parallel component, is sine. So sine of theta is opposite over hypotenuse. So I have the sine of 30 degrees is equal to my opposite side, Fg parallel, divided by my hypotenuse, which is 562 newtons. So I'll do 562 times the sine of 30. Sine of 30 is 0.5, so we get the parallel component of gravity as 281 newtons. Now, if we want to do the perpendicular component, Fg perpendicular, that is the side adjacent to my angle. So I'll use cosine. Cosine of theta is adjacent over hypotenuse. So I have the cosine of 30 degrees is equal to the adjacent side, Fg perpendicular, divided by my hypotenuse of 562 newtons. So I'll do 562 times the cosine of 30, and I get a perpendicular component here of 486.7 newtons. So there are my components of the force of gravity, right? We know the force of gravity points straight down, but it's maybe more beneficial to think, instead of maybe vertical and horizontal here, to think of parallel and perpendicular. Because when I let this cart go, or this trunk go, which way is it going to accelerate? It's not going to accelerate vertically. It's not going to accelerate horizontally. It's going to accelerate this way, right? Parallel to the plane. So it's good to think parallel and perpendicular here. In fact, let's see if we can find the acceleration of this trunk if the plane is frictionless. All right, so I'm going to redraw my plane here. Okay, here's my plane. Here's my object. I know I have a normal force which points up, Fn. And instead of drawing the force of gravity pointing down, I'm going to draw its components. So I have a component that points this way, F FG perpendicular, which we said has a value of 486.7 newtons. And then I have a force of gravity that points parallel to the plane right here, right? So I'm going to just slide this up and draw it right here. FG parallel. And we said that that was 281 newtons. So look here. If I when this trunk goes, it's not accelerating this way, right? It's accelerating down the plane. So you can make the assumption that those two forces have to be equal. So I now know what the normal force is. It's 486.7 newtons. So really, the net force acting on this trunk is right here. It's one single force pointing down the plane of 281 newtons. It's a component of gravity, right? It's this parallel component of gravity that's causing the trunk to move down the plane. So I have the net force. This is the net force. We did it. To determine the acceleration, I need that net force because sigma F equals ma. The net force is 281 newtons. The mass is, what is the mass? Oh, I don't have the mass. I have the weight. Man, why did I do that? More work for us, right? The weight is 562 newtons. Not too bad. We can get the mass. So 562 newtons is the weight times 9.81 meters per second squared. So we'll divide both sides by 9.81. 562 divided by 9.81 gives me a mass of 57.3 kilograms. So there we have it. Now I have my mass, so I'll come back to the inclined plane problem. 57.3 kilograms times our acceleration. I'll divide both sides by that given mass, and we now know the rate of acceleration down the plane. The acceleration is 4.9 meters per second squared. So, a couple of really great problems here involving the inclined plane, breaking down the components of gravity. I also did another example earlier, maybe in the warm-up question. So between those, I think you've got some good exposure to the inclined plane. And we did some really nice friction problems here with kinetic and static friction. I think this is a great place to stop. I'll see you in the next video.